Yeah, welcome back. We're up to week 3. Special lecture tomorrow. That's really loud. I might turn that down. We've got a special lecture tomorrow from Megan Dawson. You guys get a break from me. Yeah, I would encourage you all to come along and ask lots of questions. If nothing else, Brisbane is a really, really small town. And in a couple of years, if you want to go out and get a job, it's good to know a couple of people. And if you're that bright person who came up and asked lots of interesting questions to Megan, she'll remember you. And when you go for a job interview, she'll go, yeah, that person. I'd encourage you, like, I was a pretty big introvert, you know, math student, big surprise. Like, pretty big introvert when I was an undergrad, and I never would have done that stuff. But getting older, you know, I'd encourage you to network, you know, use your networks. Take this time, if you've got some people coming in from industry, to develop those and talk to people, because like it's good to figure out early what you want to do, and to get a bit of an idea, like really use it, like, you know, good person to ask lots of questions about, you know, is this a good career for me? Am I a good fit for this? So you don't end up spending a long time doing something you don't like, because you can easily do that. All right. Yeah, Megan Dawson, she works at Fugro. I believe one of our tutors did an internship. Oh, I think they were a student last year, tutor this year. They did an internship at Fugro because they're one of the local people in Brisbane who use Julia. So just a bit of a thing. I used to work at Fugro, I've got to say that. That's why they use Julia. That's how small Brisbane is. Okay, cool. Yeah, that's where we're at. Okay, so we did a bit yesterday. So yeah, we went into sorting, bubble sort as our prototypical example of how not to sort, but how to analyze complexity of algorithm. We can sort of see that it's n squared by a variety of more or less convincing means. So, you know, do the simple thing where you want to see, like, we can do all this theoretical analysis. You want to see how it runs on an actual computer, do some timing, plot it. I tend to do these types of things to investigate actual scaling a lot. If I'm doing a performance critical piece of code, I do things a lot like this. Fitting it, saying it looks like it's scaling quadratically. We do a little bit of analysis and we go, yep, it is definitely scaling quadratically. We understand that order notation. Yeah. Went through that, and then we did a little bit of probably extra stuff. I probably should just go double over again, but about comparison. And then I jumped down to the end and talked about Git. I really just wanted to introduce that early because Git, yeah, like I said, Git can be a little bit traumatic. It's like kind of renowned for being difficult to learn. It's like a really simple model underneath. You can have problems. I think I meant to show this XKCD comment because it's basically 100% correct. I'll just leave that up. Yeah, it's kind of true, unfortunately. So I showed you some of those shell commands. I'm going to do, depends where we get to today. I was going to show a bit more about using more of a development environment, a bit about Unix stuff. This is probably going to be next week, actually, honestly, on Monday. But Unix, using something like VS Code, and about software licensing, that's all going to come. But like one of the things I guess I can show you straight away is if I open VS Code, if it lets me, oh no, I updated my software. That's going to be a mistake. One of the things you'll see with VS Code, if I go to source and I go, where do I want to go? Let's go here. One of the things you get in these development environments is Git integrations. So it will say, oh, all this stuff I was doing with Git diff and adding and committing is kind of automated like it is in GitHub itself. Like, you know, you can click on buttons to make stuff happen rather than having to type these shell commands. VS Code will, not a binary file, you don't want to do that, but it will track changes for you. You can commit, you can do all the source control stuff with buttons if you like that stuff. I'm so old that I had to memorize all the shell commands. It's good to learn them so you know what Git's doing. Computers, the part of doing this course is you start seeing how the sausage is made, and really it's just talking to that thing underneath. It's doing the same things. It's just put buttons there to make it a bit easier to follow. Yeah, they can make it easier. I don't know if they actually make it easier. The best thing to do is to learn what it's doing underneath. Yeah, so, you know, Git, for better or worse, it is the dominant version control system at the moment in the world. That's why we're teaching it to you. It's not just an academic exercise. If you go for a job interview, like knowing how to use Git is like a green flag straight away, you know, so it's not for this. But again, I'd say at this point, just because it's the dominant paradigm now doesn't mean it won't be. It'll still be in a couple of years. Like these things change and you got to keep learning. So as I said, mine was Subversion or CVS, one of those two when I started working. And then it's like Git took over, and then the next thing will take over, and then the next thing will take over. It's like learning what it's trying to do is the most important thing. Then learning how to use the particular one is an important thing too. So yeah, GitHub, again, I think I tried to make this point of the internet was built by, I don't know what you want to say, left libertarians who wanted the world to be free, and everything's meant to be distributed. That's not how it actually works in practice. You know, Git is this distributed thing. One Git repo is not special. You're just trying to sync between multiple Git repos. That's the thing that makes it confusing. Nobody wants that. It's too confusing. They want one good version. So you put one repo in GitHub and use that. And that's kind of the way most software works these days. So Julia itself is a giant monster Git repo. And we didn't talk much about branching, but there's all these branches. So this is how confusing a large project will get. Same as with our stuff, like code spaces. Oh, no. If you want to clone a copy of Git of the Julia project itself, you can do that if you want, like for local development. You can do this Git clone, pull all the Julia repo, it'll be massive. That tree that I was showing when I was giving the demo last week of like, here's a commit and push, commit, push, and there's just one little stick. This will be monstrous wide thing with branches going everywhere that's impossible to keep in your head, which is what all big software projects turn into. That's really when Git gets confusing. It's like trying to sync up branches and sync up repos and get things back onto main. For you guys, hopefully it's a lot easier and a bit more gentle. You're just doing projects. There's just one or two of you collaborating on a project. You can kind of keep it quarantined by files. Has anyone had any problems with Git, using Git for the project so far, or has it been okay? Okay. Anything in particular?
I just think we're meant to be your credentials.
Yeah. That's always painful, but you only ever usually do it once. So just get a tutor or someone to sit with you and make it work on your computer. It's fine. It's like, it's not too bad. Yeah, it's always a setup is always a problem in software. So I sympathize with you. Cool. That's all I wanted to say. Part of this thing is like pull requests. So the way a typical project will be organized is you do a branch, like, oh, I could do one. No, I won't do that. That's naughty. I won't do it on a public project. You can make a branch and try and make a pull request. Whoever owns the repository will typically review the code and go, if it's good, we'll click it and merge it back in. That's typically how it works. We do this peer review in industry. It's really common to do pull requests to get work approved. So like people who work for me and me to other people. If I want to change what we're going to deploy, want to make a change to master, we do go through this pull request code review. So at the place I work at currently, which is a place called PlotLogic, we do 2 people have to approve every pull request before it can get merged back in. All this complexity is not stuff you guys need to worry about, but that's kind of common. So this is not abstract, you know, learning how to use a complicated tool for the sake of it. Everybody uses Git. Kind of everyone's aware of its problems. I think it's kind of due for the next thing to come along and take over it, but I'm not making that. So we'll probably be stuck with Git forever. Cool. That's Git. Yeah, try and use it early, I would say. Okay, what are we going on to today? So we get to do, back to sorting. So we did this comparison function one last time, where we can pass, this is like, sometimes recursion's a bit of a brain bender where you go like, I can call the function from itself. In languages, you can also pass, depending on the language, you can pass a function around as a variable too. So that's what we did with this comparison function. So back to sorting. If we wanted to define our own custom comparison function, we can do something like this. So let's go. I'll just copy this guy in, talk through it again. Oh, that wasn't happy. Copied too much stuff. That's not fun. Okay, trying to cheat and it is harassing me. Okay, so if we have a data matrix, we want to generate some random data. It's 10 long. Okay. This guy, if we go bubble sort, I think I called that X. With the default, it'll go from smaller than the smallest value to the biggest one. Generate some more data. What was it called? What did we call it? We called it comp equals. Now, this one is greater than. We can also do less than if we wanted to flip the order that it's sorting in. So there we go. It's going from biggest to smallest, whereas last time it was going from smallest to biggest. And this function, if we look, examine, well, it's just to go through the code without worrying about it too much. So we've got the normal bubble sort, loop where we're going from in1 to n-1 for j in I to n-I. We're not going all the way up because these biggest values get bubbled up to the top really quickly. So on the second iteration, we don't need to worry about doing the biggest value because that's already made its way all the way up to the top because it won all the comparisons. Before we just did this one explicitly. So we want to make this bit of software. So this bubble sort, we just had a greater than. Here we want to make it a little bit more flexible. So this is a little bit of software design, a little bit of niceties of the language. If you want to do some weird, you've got some weird data type and you want to sort it in a weird way, you just need to define this comparison function that takes 2 arguments, returns a Boolean. So any other function, who's really creative and can come up with something really weird to do for that? What's a Boolean function that takes 2 arguments and that we can do, we might be able to sort by? No creativity. No. What about, I kind of want to do something stupid. We could do equals equals. That doesn't do anything. So anyway, any Boolean function, you could do that thing. Cool, because that will always be true, right? Oh, no, that'll do something very strange. So it's easy to make, you got to be a little bit careful about how you design these functions if you're going to pass this on. So don't know what my point is there, but yeah.
How does Julia know that you want to put in the Boolean function?
It doesn't know that it's Boolean. So this is like straight up, if I saw this, I'd be a little bit scared that it's a bug waiting to happen because any function that takes 2 arguments will be valid syntax. But then when it goes, like if I go comp equals plus, say, right? That's a valid thing that will take 2 arguments, but return a float or an int, right? You'll get a method error. You go, type error, sorry. It'll go like non-Boolean used in a Boolean context. What that's actually doing is when we hit that piece of code here, we're going if 7 or something. What the hell does if 7 mean? So that's actually just a bug waiting to happen. So you'd need to be a little bit more assertive with your design that your comparison function makes sense.
It makes sense to add type hints for each of the arguments.
You don't need to do type hints. This is like, well, this is getting deep really, really quickly. It's a really awesome question. This is probably, I kind of want to do little bits of this and then talk about it. Andy can get to talk about it a bit more because I don't want to leave people behind who are, who this is their first programming language. But you don't need to do type annotation for Julia. It knows the types of all the things. So this, I think you actually, it was your question last week of like, how do I trigger type instability? That's probably another one. Julia can do type promotion to type any, and it looks through all the methods and goes like, oh yeah, I can do that. Plus makes sense for these 2 types. So you can work all that stuff out and it's really fast. Type annotation is more for triggering multiple dispatch. I'll talk about that a bit later because that won't make any sense to anyone. Yeah, like you could do like the type annotation version of that, but you'll still get it. You'll basically get the same error because you'll go something like this guy is of type bool. But you know, that won't do much. Like you can also do it like because you're trying to in this code itself, you're trying to parameterize the type of the comparison function that's allowed valid as an output. That's kind of a bit harder. So you could assert type there, go like this is going to be a type Boolean. I don't think that'll do anything other than the type error gave you. It'll just do the same thing. It goes like, oh, that's not a bool, so no good. You're not allowed to do that. Does that make sense? Half answer your question? Style, but this is the thing. Usually, like there's a certain type of developer when they first learn Julia, they'll type annotate everything. You don't need to do that. It's like, it's good for catching errors. Like if I go, if I'm writing a function, say like calls plus A and B, and I only know how to do this with int for some reason. Yeah, because I know plus how plus works for int. If I go polls, can't type my name, polls plus, if I go 1, 3, that's all good. But if I go 1, 3.0, it goes method error. You can't do that. There's no function that works for anything other than type in. So if you're trying to sanitize inputs, like catch, that can be useful, like to guard against like improper use, but you'll get this weird method error that will confuse people anyway. No, the style is like using it judiciously for multiple dispatches would be what I would say. You see some of the code, I've done it in some places. Like I think on the first lecture I did it with the adder circuit. I've added type annotation to go like, this has got to be subtype Boolean or it doesn't make sense. That's more to catch this kind of improper use, but you still get this method error thing. So, make sense? Cool. I had another question on this one. I think I want to answer it about how to induce type instability. And I had a brain fart and couldn't do it in the lecture last time about like, if we want to go, you were saying about code warn type and like, what does type instability look like? That's another thing that might be useful to talk about now. I've said this thing about there's this useful function code warn type where it'll give you red. I'll give you an example of that now while we're just talking about types. Julia is fast if it doesn't have to promote to this any type. So if it can work out what's going on with functions, it'll be really fast. The cases where it doesn't go fast is where it goes like, I don't know what that is. It could be anything. I've got to promote to the any type and check all the functions that might exist against that type. As soon as I walked out the lecture, I thought, I can make it. I can make this. So wonky func. Okay. So let's say we go if mod x2 equals 0. Everyone familiar with mod? If I say mod, what does that do? Anyone not familiar with mod? Mod? Anyone want to answer what mod is? Or we can just show it. So mod, if you always want a hint, go to Julia, !mod. It will say, oh, it's got lots of different types here. So this is a bit confusing with the type, with Julia help, it'll go, this works for an abstract unit range. That's not the one we want. So it's the reduction of x modulo y or equivalent the remainder of x after flawed division by y. Does that make sense if we say it that way? Yeah, cool. So if I'm going mod 1, 2, what's that going to be? Anyone want to guess what the answer is? 1. And if I go 2, 0. And then 3 goes back to 1. Anyone else familiar? This is another one I've said. I think I said about like, as a test, if you ever go for a software job, like one of the things to get in the door is if you know what a ternary is. Has anyone heard of a FizzBuzz test? You know a FizzBuzz test? FizzBuzz test is a coding challenge they sometimes give people. It's another one of these ones like, do you know what modulus is? Like, have you seen this before? Do you know how to use it? It's like, you go, I want to give you a range, like from 0 to 100, say. And if the number divides 2, I want you to print fizz. If it divides 3, I want you to print buzz. If it divides 2 and 3, I want you to print FizzBuzz. So that's like a little simple coding challenge thing that people do. And it's really like, do you know what mod is and do you know why it's useful? Because you should be able to see that if you know this mod function, it's kind of trivial to make a fizzbuzz. You can do that. Anyway, that was that. It was all over the place. Oh yeah, type instability. Function, wonky, x, if mod x2 equals 0, y equals 3, else y equals a, and return y times 9. Okay. And yeah, there we go. So it's going to take something x. We can do this type annotation if you want. As you said before, you don't need to do this, but if you want to restrict it to the ints, you can do that. That says x will be an int. And what we're going to do here is if the value of x equals 0, oh, sorry, mod x2 equals 0, if it's a 0, 2, 4, we're going to make y equal to the integer 3. Else we're going to make it equal to the string a, and then we're going to go return y times 9. So that's a little bit weird, right? Because we said, what does times mean if it's a string, and what does times mean if it's an int? They're two different methods. So this is one where we can probably you just go space, wonky 3. So this one's less, this is one where it's gone like y is going to be, this is like, last time I was showing it, it was all blue. This is like a hint. It's not super bad, but this is going, oh, y is going to either be an int or a string, because if, and then when I go to do the z bit, I've got to worry about what that's going to be. And it's going to be an integer again, but it's like, oh, I don't really know what y is going to be in the middle. This is one of these cases where the type hint, the code one type can give you a thing. The one that you guys are actually going to get, and I think you've probably already gotten it if you're not careful, because this one comes up all the time, is if you've done a script and you haven't wrapped things in a function. Sometimes, I probably haven't harped on about this enough, but if you want stuff to go fast in Julia, wrap it in a function and pass all the arguments in, because then Julia can work out what's going on. If you've left something, this is another example where we can get type instability. So we've got a value x equals 3, y equals 4. I think I had x, y. Okay, we can do that. If I do code one type, that's cool. That's all blue. It's going to be super fast. If I write false plus 2, and I don't pass b in, like this is so easy to do, right? Like you write a function and you have an argument and you sort of secretly hidden it there as a global. You can't work out what the type of b is going to be. If I run this, it'll probably work. Oh, b is not defined. So depending on the type, this is the one where you're going to get, oh, there's something globally called b. So if I said b equals, so I can say what b is on the outside and then this function will work. So that works. But if I do this code one type, it's still going to complain because it's like b is in the scope outside this program. And I don't know if that's going to change on me. So I can't specialize on the type for that plus. This one is really easy to do, and you'll probably do it when you're writing scripts for your homework. So like if you're trying to do, say, the goldback one that's really slow, wrap it in a function, pass all the arguments in because it can't figure out what the type of the arguments are and everything goes really slow. That's a really big sidetrack, but hopefully that helps. Okay, good. Okay. All right, so yeah, we can do some funky stuff here. So this one is, we can make an inline function. So we got back to that comparison function. We can go, my comp is going to be based on whether the sum of the digits is greater than this. So you can make a much more complicated comparison function. Sum digits. Okay, I probably need to be careful about the data here because I wasn't doing ints. Okay, so bubble sort comp equals my comp. So we're all happy with that inline function definition. You can do that. It's nice to do one-liners sometimes. Sometimes it's really ugly. I think in the homework, we've got you to do one that's, we'll ask you to do stuff that isn't necessarily the nicest way to look at it, but you can try it just so you understand how to write these things. Then what this one's going to do, we've got this digits function. Going to get the digits of num1 and we're going to sum those up. Digits of num2, sum that up. So x, oh no, we don't want x, we want data. That doesn't even make any sense. Okay, so the sum of the digits of these guys. So original data, if we want to know what does digits do, again, ask that guy, ask the thing. It turns an array with the digits of n in a given base. So it's going to default to base 10. So it's going to sum, so 6 plus 5, 5 plus 1, 3 plus 2, blah, blah, blah. So the biggest one is 6 plus 8, hopefully, 8 plus 4. That's right, that's correct. I just had to check. Yep. So what it's doing is turning those into the digits and then summing them up. So that's cool. So you can make that, you can do all sorts of comparison functions. The next one that's a bit of funky syntax that I wanted to show here is there's this thing called an anonymous function. Has anyone heard of an anonymous function before? Not heard of an anonymous function before? Always that thing. It's like, it's in the name. Sometimes you don't want to be bothered writing out the name of the function. So it's a function without a name. That's all it is. It's not any more complicated than that at this level. So in this guy, we had this comparison function, myComp. Sometimes you just like, the only time I'm ever going to use this function is to pass it into another function. So there's no point writing out a whole definition for this function. I might just write out a function in a one-liner to pass it through to the next one. That's the idea of this anonymous function. So what we could do instead, we'll go to this one. I'll get data back. We can write an anonymous function, x1, x2. So that you can imagine, I've got it in this tuple. You can think of those as the input to the function, but I haven't said what the name of the function is. And then this little wonky syntax where you go like a little arrow dash thing, and then you can go, it's just this second bit. So we're doing exactly the same thing. Probably made it a bit. Can everyone see that on the big board? It's stretching the definition of a one-liner, but it's still a one-liner. So this is exactly the same. And hopefully, oh, num1. I cheated because I half wrote it myself and half copied. So that's why you got to think about these things before you do them. So x1 and x2 are our arguments. We want to pass those through. Does the same thing. So this is called an anonymous function. Anonymous is in a function without a name. I don't use them like this. What I use them for, I've probably shown you this before, is I've gone like map, x goes to x squared 1 to 10. That's an anonymous function. If I wanted to do, let's think about that. That's the typical use, is like map and filter. You define anonymous functions. You can also pass a function in. I could go function my square, blah, 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 blah. You know, you get the idea. Yeah. Any questions on anonymous functions? Did that make sense? A bit weird? You'll get the hang of it. It's really this thing of like, I don't want this thing to hang around. I just want to do it as a one-off thing. Make an anonymous function, pass it on. Okay. There we go. And you can also, we have this begin in, I'm not going to even copy this one out, but I can just say, if you want a multi-line anonymous function, you're starting to get to the point of like, what are you doing? Don't do this. Just write the damn function name. You can do begin end to enclose a few more lines to make it a bit neater. That's what's going on here. So basically, we've got 2 lines to this function. We've got this global counter, and we're doing this sum, and it's going to return the, like we haven't got a return thing here. Remember in Julia, if you don't say it, it'll return the last line. So it's still going to return the same thing, but it's also got this global counter increment. So you can make, this is this begin in syntax. It's like you can define little bits of,
Does that work in like ternary operator as well?
You probably could. I've never tried it. You can have a go. Yeah. So same thing. You probably can do a begin-in syntax. You can probably pass. Better thing to do is if it's starting to get complicated, write a function. That would be my advice. So you can pass this through to a function instead. If it's getting complicated, there's this like. We're going to talk about data modeling in a second, but like there's always this tension of like, oh, I just want to do it now. It'll make it work, but it's a bit ugly. Whenever you see that, if you get that bad feeling, you probably should go off and write a function. It's kind of the way it goes, but I can understand doing it. Any other questions on the anonymous function thing? I think that is in the homework, right? You have to do something like that, I'm sure. Or it's a nice way to do it sometimes. Again, for me, takeaways, filter and map. You know, if I want to go filter, we just did mod 2. Oh, x goes to, I've got a filter. I didn't put my equals 0. So if I wanted to get all the even numbers, I could do that. And if I wanted to get all the things that divide by 3, I can do that. That's where I use anonymous functions all the time in filters and maps. That's really the natural use for that sort of stuff. Cool. Okay. I think I'm happy with that. Okay. So we did this depressing analysis of bubble sort, and it's like thousands of times faster depending on how big your array is. It scales really badly. We've got a hint that the inbuilt sort is much, much faster, and we'd like to know what the hell it's doing to be so much better than us. We get this hint that we do dirty software engineering tricks, like putting that inbounds macro to try and make it like stop doing sensible things that will make you do good error checking. Doesn't really make it that much faster, so it must be doing something algorithmic. It's like, if you can rule out type instability in Julia, algorithmic is the next thing. And all of the big wins in software are algorithmic tricks, honestly. Like you look at the history of like linear programming or something like that. It's like algorithmic improvements have kind of outpaced the, you know, like computers. I think I've said this a lot. When I was a teenager, computers measured in megahertz. Now they're in gigahertz, and there's like 8 of them on one computer. It's not even one computer. It's like 16 or 32, or depending on how many threads, how many cores you've got. So hardware's gone incredibly fast, but there's been, in lots of areas, the algorithmic stuff has sort of kept pace. Like in difficult problems, if you can fight, you can't make hardware, like Moore's law is a thing that people talk about transistor counts, that kind of died, but how much faster computers are getting over time, you know, they're exponentially increasing, but if you're trying to solve exponential problems, you'll never win. Like that scaling law will run out. You have to do algorithmic tricks to make stuff faster. So doing the smart things is the way to do it. Okay, this is a little bit of timing. This is basically the same as last time. We did this time nanoseconds. So I'm not going to bother saying about it. But we're interested in doing this timing for the built-in sort function. Sorting is very important. So it's important. I've said it's not, I don't care that much about it, but it is important. You use it all the time. There are so many sorting algorithms. Like here we go. Quick sort, merge sort, in-place sort, into sort, heap sort, insertion sort, block sort, team sort, selection sort, blah, 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 blah. It keeps going. More. There are heaps of sorting algorithms. It's like a zoo. I think, I could be wrong, but I'm pretty sure Python uses Tim sort and Julia uses quick sort, just as a difference. So it's not like even a settled thing about which one's the best one to use in all applications. Yeah, we're interested in what the empirical performance of the built-in sort function does. And so we do this thing where we're going to record the start time in nanoseconds. We're going to run sort. We regenerate the data with the same random seed. So we're sorting the same thing every time. And we plot this as we go up, and cool. Does that look quadratic? Anyone got a feeling for these things? You're not going to get it wrong if you say it wrong. Maybe a bit-ish. It looks like it's not linear. Is it linear? Not quite, right? Like, so it looks like it's like super linear scaling. So it's a bit more than linear. The running time actually grows n log n. So like this is pretty famous complexity class. N log n on average for the sort function that's built in is what we'll see. Part of the homework is to do this yourself. You have to do your own implementation of sorting. So I'm just going to kind of give you an overview when we get to this stuff. We're going to go through two. We're going to talk through two in semi-detail, but not too much detail. We're going to go through one that's a trick using a data structure. So I haven't said what a data structure is yet, but one heap sort is the one that's fast because it uses a nice data structure. And the other one is a kind of clever algorithmic one called merge sort. You can actually go to the source code here and find out what sort's actually doing. There's a little, this is a hint about, you know, I was saying like sometimes you just want to check if the function, if the array is sorted before you even start, so you can do this early bail. So having a function like is sorted is probably a good idea. You can get an idea of like, this kind of stuff might seem a bit weird. I think we talked about this. There's this LT equals isless by identity, rev for reverse, order, ordering forward, blah, blah, blah. This is like, I'd say, design of the function. People have probably thought about this for a long time, so you can steal a lot of good ideas when you see how other people actually do things. What do you mean by less than for your type is what this is less thing is. I might talk a bit about this in a second. And you can go and see through. Anyway, won't talk too much about that. First, we're going to go in on what is data structures. Probably got 10 minutes where I can really realistically talk about that before your brains shut down and we have a little break. Data structures, what are data structures? We've only talked about really, really basic data types. And a data structure, the idea is that maybe if you're clever in how you construct the data in the first place and store it in memory, all of the work is done for you when you go to use it. That's the idea. So this is the idea of a data structure. Anyone come across this? Anyone done a data structures course and knows more than me? You'll be bored. Yeah, this is a really powerful idea of like, this thing I was saying when I worked at Fugro, where Megan's coming from tomorrow, this is a real problem of like, I have a LiDAR scan of all of Queensland. It took a whole year to take that scan. Like we had 4 planes flying all year for, all day for a year to scan all of Queensland. And we did that every year. And then I'm going to go like, at this point in space, give me the 10,000 closest points to this space, to this point. How would you do that? Am I going to sort all the points by radius to do that? Even if it's n log n. Like we had, Megan, you can ask Megan tomorrow, but when I was working, that was maybe 40 points per square meter. And we had all of Queensland. So you can imagine how many points we had. So like, this is a really natural query to want to do of like, how can you actually do that efficiently? So first question would be, do I want to sort all the points or do I just want the closest ones? They're kind of different things, right? Like, I don't really want to go like, you know, calculate the radius from this point to every other point. I can probably do things that make it easier to do. I'll park that there and I'll talk about it a bit later. But that's the idea of like, can you make a data structure that the way I store this data makes those queries efficient? And for that one, I'll jump to the answer and is, you keep little blobs of data that are close in space, that are bigger than any radius you're going to query. And then you go, cool, if I get all the ones in that one, it's much less than all of Queensland, but then I just sort those arrays. That's that point. So data structures, kind of this trite thing, don't confuse data structures with databases. I think Andy will talk to you about databases, what a database is. Database is kind of data with a data structure. It's this thing called a B tree. Andy will talk to you guys about that later because SQL is a thing. It's a big thing. Okay. We've already seen this one and I've done it, shown it to you heaps and heaps of times, but you probably haven't thought about, maybe you have, depends on how your brain works, but I keep doing this thing, making an array, right? And there's this idea of these things in this array that have an order that makes sense. That there's a first, there's a second, there's a third, or there's a zeroth, depending on if you like array indexing like that. I'd say there's a first. And I might want to get the first element out of this array and like, cool, how's it actually doing that? Like, And I probably want that access to be quick. If I want to get any one of these elements, if I want to get the third one out of the array, I want it to be really fast. I don't want it to be slow. So what is this thing doing to do that? And like, as a mathematician, you know, this is kind of like a vector, but it's not really a vector, is it? Like, because what does the transpose of this thing mean? Like things like that, you can think about that. So they give it this, you know, they say it's a vector of type. So let's look at, we'll just reproduce this data again. Now, we've got this function, a useful thing to know. Hopefully you've seen this one because I've done it lots of times. Length of data, there's 8 elements. If I push something onto that guy, push. You know, it's gone up to 9 elements long. Okay, and we can get any element we particularly want. So the important thing here is when we've talked about this big O notation, any lookup, we want to be super fast for this thing. So the way these are implemented is they'll be order 1, it's constant time lookup. Doesn't matter how big the array is. If I want the nth element, I get it straight away. And it takes the same time to get the nth, to get the n plus 1th, to get the first, last, blah, blah, blah. That's the kind of, if you think about the design of the data structure, that's the kind of thing we want to be super fast. Other things are going to be slow though. So this thing where I just pushed onto the array. So like, if I want to make this thing bigger, I'm going to have to allocate more memory. How's it going to do that? That might be slow, that might be fast. We kind of want to, like, I think I've talked about this, maybe less this year than other years, but like, you kind of can't get away with abstracting everything away from how the computer works. So you probably want these things to be close in memory as well, physically close in memory when you're making an array. That's why you kind of don't get a choice about push being a bit slow. Yeah, so some useful functions. Type of, done this one to death. Type of data, it says it's a vector of int64. This other one, L type, gives me the, gives me int64. So for the elements of the array, what's the type of those things? This one is super useful. Has anyone had to do this? This is one where type instability, you go like, oh, I've got data and I've got this working array and I want it to be the same size. And I want to fill it with zeros to start with, say, like I'm going to make a counter for each element. You can go zeros, L type data, length data, super useful. That will make zeros that have the same type, because if I do zeros like this, they'll be float 64s, and that will be a way you can get type instability creeping into your code. So that's useful, L type. So you get this idea that the data, this array, it has its type has this base type of the elements. Now this one's a bit weird. Pointer. Does anyone know? Anyone heard of a pointer? Not heard of a pointer before? You not heard of a pointer? You have heard or haven't? Haven't heard of a pointer. And no, who's a C programmer? Anyone? We got any? This is like something you want to steer clear of if you have to worry about this stuff. Of like, where is it pointing to in memory, where this bit of data is? So we'll get this funny, if I say that, there's a funny at thing in there, but X, what does that mean? What's that mean it's code for? X. So this is actually, data's actually in there at that spot. So there's an address in memory where it's going like, oh, there's your data. You don't need to do this with Julia because it's this garbage collected high-level language. You don't need to worry about where things are in memory. You don't need to worry about tracking memory. But if you want it and you want to do some weird shit, it's there. Just avoid it. Okay? But this is more for how this thing's going to go. So what we can see here, we've got pointer to data is here. Pointer data 1. This is the first thing in the array. Second thing in the array, Who can tell me what the difference between those two things is?
Just the 8 at the end.
8 at the end. What might that be?
Size.
Yeah, so if we go size of x is 8. So this is these things. It's like, oh, there's that bit of data. Then next to it is this bit of data. Next to it is this bit of data in memory. So we can do that for all the elements in the array. Data 5. You can see through all the way through. Cool. I think we've done that a bit. Yeah. Cool. So that's just a bit of a hint for a vector. So this is the first type of array. Next thing we're going to do, though, yeah, if you want to go hard and go look at some more stuff, typically as soon as you learn an array in a course like this, if it's a course about data structures, next thing you go, linked list is a really useful data structure that's based on arrays. Queues, stacks, blah, blah, blah. Not going to teach that here. I'd be the worst person to teach it as well. But, you know, if you want to go off and learn, I totally encourage you to learn this stuff because it's useful. We're in a very high level language here. So like if you're in C, not C++, C, you don't get many data structures by default. You kind of have to make them yourself or import them. So you kind of got to learn how to make these things from scratch. We're in a higher level language. So all that stuff's given to you for free. You don't need to worry about it. You can just think about it as a vector. You don't need to know what it's doing with memory, but you kind of do, which we'll go to in the next bit. Yeah, next one though is multi-dimensional arrays. And if you ever want to make a physicist mad, call it a tensor. It's not a tensor, but it is a tensor. You can think of it that way. So multi-dimensional arrays. So if we're going to go, you know, the normal one for a mathematician is a matrix, right? So we can make data equals, if you want to make a matrix, that's the first row, and then the second row, 6, 7, 8, 9. You can make a matrix. You can also do harder to set up, but you can do a 3-dimensional array. You can do a 4-dimensional array. You can use an n-dimensional array, bigger and bigger and bigger, depending on what your problem is. But normal mathematicians, you can get a long way with vectors and matrices. So what we're going to do here, again, we saw this funny undef, like if you want to make an unallocated array, we can do this. So this guy makes a matrix of undef type for int 8s that's 3 by 5. So that's what M and N is. So this is a way to set this up. Another useful way to do this, if you want to construct these arrays, is with a comprehension. You can do the same thing as we did before. You can make, you know, initialize these things with a comprehension. Undef is useful if you don't know what it's going to be yet. Like you could do zeros. So that thing I said, zeros, L type, data, could have done this. No, 5. That'll do the same thing. If you want zeros, but this, if you don't actually want it to be 0, if you want it to be undef, you can do that. That's cool. I'll just quickly do this one. What we're going to do is n times m is the total size of this 2D array, this matrix. It's not really a matrix, it's a 2D array. We can go through, we've got some funny stuff we can do with this guy. I'll just say quickly, the natural thing to index into this data would be to go like 1, 1. What's the I? Just to check. This data is a bit boring. I'll make this data a bit better. Let's go 1, 2, 3, 4, 5, 6. Okay, data 1, 1. So you can see that is 1. Data 3, 1. Oh, can't do that. We can do that though. That's 4. So going down in that first axis, 1, 3, 2, 3. There's data. You can also get a hint that you can do a linear index into data as well. You don't have to do this 2-variable form. I can go 1, 2, oh, 4. What am I doing? you can also do, you might notice this pattern too, how this accesses this data. So if I do this linear index into data, I don't give it the 2. It'll go 1, 4, 2, 5, 3, 6. Let's just check that isn't a fluke. Make a slightly bigger thing. So 4 times 5. So we should be able to see that it's going this one, this one, this one, this one, this one, this one, this one. Then it rocks up to this guy again, goes down, 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 down. Okay, that's all right, cool. I'll just leave you hanging with that mysterious bit of information and we'll just have a break for 10 minutes. And then after this, we'll go through why it's laid out like this. Well, I guess it has to be laid out a certain way. And more importantly is the consequences of the way this array is constructed. Okay, I'll leave it there.
Yeah, it was about education.
Oh, yeah.
Also one of those. It's I can't pull from my terminal, from GitHub or push, but I can do that on VS Code. And I don't know what happened. I was because the tutor wasn't familiar with SSH. And
Did you set it up via SSH?
No, I didn't.
Oh, you did GitHub
I tried to, yeah.
Okay, that's okay.
If you want, I can show you on the laptop, but
Yeah.
maybe someone else want.
If you bring it over, I can't say I'll be
No,
quick at sorting it out, but it'll be should be something simple.
Okay.
Yeah.
And also another thing, it was just applied to that. I had set up a GitHub account with SSH on a computer. Is it possible to bring the SSH from one computer, one machine to another?
Yep.
Yeah.
You can just private key you'll have
Copy
you
the.
can copy that link. Yeah. Just be careful.
Yeah, it's wondering.
I'm having just on the homework question 12.
Okay.
So just reading off this, and it's like trying to count the number of characters in each cell.
Yep.
But what it's doing is like from the source here, where the actual text is. Since like it's like all the text is sort of like in a list, I guess.
Yep. It's an array.
And yeah,
Oh, is
so
No, okay. Yep. Got it.
I have like a way that I'll be able to like iterate through each of them and just add all the characters together. That is working. Is that what we're supposed to do, or is it only supposed to like look at the first one?
I can't remember the wording of the question, honestly.
It said basically just like determines how many characters total are in the cell.
Yeah. Okay.
Okay, so I'm adding all of those separate ones.
Yeah. That's
Okay.
fine.
So that is fine. The issue that I don't know how to solve is it'll count it almost exactly, but it's not counting backslashes specifically.
Yeah.
Like
Okay.
it'll return there's one character here instead of 2. All the other like sort of non-numeric characters work.
How are you
except
doing it?
that's the solution.
My question.
Yeah.
So we're going through the like I'm just going from 1 to 1, so it's only looking at the first cell. And this is for markdown cells only. Character 0 position is permitted it's actually chat itself otherwise. Markdown cell array I, so that's just the first markdown cell. The length of cells in source, so like the length of
Yeah. So source is an array.
Yeah, so just the length of that,
Right,
and that was
string.
like 9, I think. Yeah,
Yep.
it's returning 9.
Cool.
And then for J in that array, characters equals characters plus the length of that string. And it's returning like almost exactly the right thing each time. I just checked for like copying it into a Word document and seeing how many characters there actually are.
Yeah, so it's those characters like the -n is a new line character.
Yeah.
So that's a special, we would probably just count that as a single character.
Okay.
So that's actually fine.
Oh, okay,
Yeah.
cool. Yeah, because they said in this specific part that I was like, okay, so it wants us to count that. Does like should it be counted as 2 or what?
Determines how many character count determines how many characters.
But that's still.
Include characters such as -n. Characters as single. Okay.
Yeah, so it would just be counting like backslashes sort
Yeah.
of appended onto whatever it's attached to.
Yeah, I think
It's
that's
just
okay. Sorry.
That's fine.
Yeah. Alright, in the sound, include characters such as dashing. Okay, that sounds right, like you're doing the right thing to me, because you're just doing length and it's the Unicode characters.
Yeah.
You could do something different, like you could parse it, right? Like you could get the, instead of doing like assuming this length thing is right, like maybe look through what this type of this thing is, and there might be something different you can do if you wanted to do something different.
Okay. I did use parse at some point, but only like to the extent that it was shown in the notes. Because obviously we haven't done this yet. We've done this last time.
Yeah,
Totally sure how to use
but it
parse
sounds,
sort of in that context.
it sounds like you're doing the right thing to me though. If you're worried like particular, just ask a question on Ed and the onion because he's
I think I did.
more in charge of like the exact, if I saw what you did, I'd go, yeah, cool, that's good.
Yeah, okay. Cool.
How are you finding the course? You're a bit worried at the start.
Yeah, I mean I feel like I'm bashing my head against each question until it works, but it is sort of working.
Is it getting easy? It's that's what it's like, and then it'll all click and get easier.
Yeah, you do get more used to it as you go, I guess, even as the questions get harder. I am doing the odd numbered one, so partner's doing the evens.
Yeah,
I
just
feel
make sure
like
you
a lot of the
review what they
evens
did.
are, yeah, I definitely want to go back and actually make sure I understand what's going on there.
You get the cool questions.
I didn't want to do the planetary motion one because I don't like it, so that's why I'm doing that one. Well, it looks cool. I'm scared of it.
No.
Yeah, the rest of it's okay. I've sort of been, that's the wrong thing. I'm doing like 10, 11, 12, so the like GitHub units and all of this
Okay.
fun stuff. It is, I think it's working.
That's good.
I get a result that doesn't seem completely ridiculous. It's just the volume of
Yeah, yeah.
questions to try and get
It's a
through.
lot to get through. Oh, it sounds like you're doing well.
Yeah, thank you.
Specific things like that, just ask it in the only
Yeah, okay,
but it
thank
sounds like you're doing the right. Hey, I just squashed this. This is going to be a disaster. I'll hold it here.
They're pretty durable. They survived like 30 years ago, right? So I'm on, I like put the whole weekend into question 6.
Oh no.
And it culminated on Sunday with me leaving the function running for 500 minutes, in which it was not done.
Okay.
So I was wondering, like, because you mentioned the like getting rid of the promotion sign for like an unspecified type.
Yep.
How do you like implement that? I tried while you were talking and it just messed up. I was just like, okay.
Hang on, let's, do you don't mind me looking through what you've
Oh,
done?
no.
Okay, so you got this sieve of RSAs.
Yeah, I didn't change this.
Okay.
This is weird. I think my yeah. So, funky online.
Yeah, okay. So the trick is sieve output. So check go back to end. Where are you running this guy? Yeah, so the trick is, first trick is like, think about how many times you have to run that sieve function. Like, do you need to do that
Once.
So when you're doing this broadcasting, you're running Sony's n for each n. Whereas if you look at how that function works, you're kind of recalculating a whole bunch of stuff you don't need to do every time. Does that make sense?
Right.
Try running it for like a few, like low ones, and check how that sieve function works.
Yeah.
And whether you're doing any rework, like have you found primes, like the primes, if you're doing the primes up to n, and then you do the primes up to n minus 1, n plus 1, and you run that sieve function for each one, all these ones you calculated before, you have to do that again anyway.
Right.
Does that make sense?
Wait, I think I misunderstand how the sieve function works. Oh, I get what you mean, because the sieve should have looked harder at this. So the sieve function is actually like counting from the bottom prime and like going up each time.
Yeah.
When it could just go like.
Well, if you only need to know up to so n primes, so just do that once up front, get all the primes up to blah,
Yeah.
and then start working with those. That's a big, yeah.
Right. Okay. All right. I'll try and action that in.
So let's take a quick one.
Okay.
Do you have any like recommendations on sort of like that question to have like a constructive approach, like constructive edges, or actually that's like fine?
There's lots of ways you can do it. I'm the class came up to me before and he'd done a really creative way. I haven't heard that before. I was doing it. Trick I give the broad hint is like you only want to calculate that set of primes once, and then think about how you could iterate over those, or iterate over. Think about flipping around the order of iteration is the biggest thing I can do. Try and only do things once if you can.
Okay, let's see if this thing stays around. Everyone ready to go again? Cool. Okay. Chat is silent. It's good or not good. Everyone's keeping up. Okay, so let's go back to this guy. Okay. Let's just run this in our code. So what this is going to do, apart from be badly formatted, is we're going to go through data using this linear indexing and check how the data in this matrix, in this case, is laid out in memory. And we'll see, again, we've got this, because, data's a little bit special this time. So what was the L type? Who's got a good memory? L type of data is an int 8, right? So before, when we were doing int64s, they were 8 bytes apart in memory. 8 times 8 is 64. Now, because they're only int 8s, they're only going to be 1 byte apart in memory. And you can see this in this hex thing. They're going 8, 9, A, B, C, D, E, F. Who can count in hex? It goes up to 500. 0, 1, 2, 3, 4, 5, 6. So we can see, if you can remember, data, it seems to be when we do the linear index into data, data 1 is 1, data 2 is 2, data 3 is 3, and then it will click back around to 4, data 4 is 4. Okay, so this, you have to choose a way to arrange the array in memory. So you get this choice, this freedom of choice. You could have everything going this way, you know, we go columns first and then we do rows, or we can do rows first and then we do columns. So this kind of ends up being a semi-arbitrary choice in programming languages. This has consequences. So this is a choice in Julia. They've like decided two-dimensional arrays or multi-dimensional arrays are going to be iterate in that dimension first. So column major versus row major. And this, we'll see a little bit later, has a consequence. This is just this thing again that you can do the linear index. And if you wanted to calculate what the linear index was from these two, this is what the equation would be. You're just going to go for J and this. So you can do, sorry, this is another bit of syntax I'll go through. You can do 2 iterators in a row. You can go for J in I to N, I in 1 to N in one line if you want to, or you can do 2 for loops. I tend to always do the 2 for loop version. We can go, cool. This thing and this thing are the same thing. So these are different ways to access the same thing in memory. Really underneath though, if we look at this pointer of where this thing's pointing to in memory, it's going to, you know, this is the way it's laid out. I hope that's clear. Okay. This has a really important consequence though, because we said it's order 1, array access is order 1. But this is a physical device. And unfortunately, things that are close in memory will be faster to access together than things that are far apart in memory. Even though we call it RAM. Anyone know what RAM stands for? Like random access memory. So it's meant to be a device that you can go like, I can give it any pointer, any address, and it'll get the memory back as fast as it can. Not true. Things that are closer together will come back closer together. And you have these things called, has anyone mysteriously looked at computer specs and gone like, what's an L1 cache? What's an L2 cache? Have you seen that in CPU specs ever before? You have? Do you know what it means?
Like the L1 is the fast one.
Yeah. Yeah. So that's exactly right. So there's a hierarchy of memory and how close it is to the CPU, and things that are in the cache, you know, it can use that memory quicker than it has to go far away, get this thing, it can't load it into the cache. So you can do a thing called a cache miss. And if you're striding through the matrix in the wrong way, one way will be faster than the other, depending on the shape of the matrix, because of the way it's laid out in memory. We've got a demo here. What we're going to do is, we've got 2 functions here, sum rows, then sum columns. So what the idea is, we've got some data, we've got the size of the data. Sorry about this, this is pretty terrible code, because you can just tell this from the data, but anyway. We've got a thing that's a 0 of L type of data. So again, it's getting the base type of this data, and it's going to put a 0 of that. What we're going to go through the array, and the only difference between these 2 functions, if we look, for I equals 1 to n, and for j equals 1 to m. So it's which one is the fastest, you know, is the fast way through the matrix? Which one is, you know, we're iterating quickly this way or quickly this way across the matrix? Does that make sense? Can everyone sort of see that? Cool. I will run this code. Let's see what happens. Okay, we run up to here, just a bunch of code getting copied across. So you'll notice I've cheated to make this I've cheated by in the shape of this thing. So who can, if you can see this, you know, this is a really, really funnily laid out array. So it's 5 really narrow compared to the width. So it's 1,000,000 wide, 500 long, because I'm trying to really make this cache miss happen as hard as I can. So what we're going to do is we're going to time these 2 things. So again, as I said, this is pretty dirty to do this. So we're going to sum over the columns first, and it takes 0.78-ish seconds, a little bit of indeterminism because, you know, it's a real computer, there's other stuff going on in the background, it's got to clear some memory sometimes. And if we do sum rows, you can immediately tell that it's not happy, right? 7 seconds. So it's doing the same thing. It's just iterating through the array in a different order. It's going this way fast, or is it going this way fast? And because we saw how the memory is laid out, where if we go down the array, they're close to each other in memory, it's going to iterate through the array much faster if you do that access pattern. So the whole point of that is order 1 is not order 1. You know, there is a coefficient out the front sometimes, and it does depend on details of the implementation of the thing you're using. Julia, they've chosen to arrange the matrices in this way so that in memory, you guys have seen this, data 1, we look at data, you know, this giant thing. This guy is closer to, in memory, is much, much closer in memory than this one. Like if we looked at the pointers for these guys, this way is a long, long way away in memory. So you're going to get these cache misses, it's going to be really slow. So in this case, 10 times slower, which is big enough for me to care about if that was a real problem. So don't know if you'll see this one. I've had this one come up in the wild often, like when you're doing numerical linear algebra, you get a choice of like, do I want to arrange my matrix this way or that way? Sometimes it matters. like which way you do it. Cool. And nearly, so the one to think about though, so like, has anyone done too much MATLAB? Has anyone been traumatized by MATLAB? Is that a thing? No, that's a deadline. You have? You don't need to make everything a matrix. Like that's the one in Julia. So you can totally make an array of arrays. So this will be, again, I'm thinking about point clouds. If I have each one of these, you know, I can have a matrix, a vector of vectors. That's another thing you can do. And sometimes that's far more natural, and then they'll all be close together in memory and do the right stuff you want to do. Making this as a matrix when it's something like a series of points is not the right thing to do. This is something about data types and what types mean. You know, it would be easy to not think too hard and go like, oh, yeah, I'll just make it a 3 by n matrix, you know, of points, when it's not really that. It's an array of 3-dimensional points. That's a bit weird. Okay, cool. So yeah, timing, my computer's a bit slower than Yoni's computer apparently, so that's the same thing. So he gets 0.6 and 6. So yeah, cache misses by rows, even though it's order 1, doesn't really mean that. Okay, now we've got another special data structure. We've seen this one before, and I was kind of segueing into it last time by saying, like, you know, if I've got something like points, it's not really a matrix, it's an array of arrays. We have this complicated problem. I'm going to sort of farm this one off to Andy as well, where thinking about how you model data, not when it's more complicated than low-level types, is a really difficult problem. I'm not going to pretend that it's easy, and it's actually a really common source of problems when you're doing professional software development, of like getting the data model wrong is like, and then having to live with a slightly broken data model is really hard and really, really complicated problem. So here we might have, I think I've talked about, maybe people can't remember, I might have introduced a name tuple in a dictionary before. Name tuple, we've got normal tuples, where we go like 1, 2, 3, A, that's a tuple, but I can also give these a name. Int1 equals blah, int2 equals 2. I can't be bothered doing the rest. That's a thing called a name tuple. There's a really flexible, there's another thing, I would kind of want to introduce this too, is like, if you really want to bed down a type, you can make these composite things called structs. And Andy's going to do this stuff with you. So anything I introduce here, just kind of like so you can see it. Say I want to model, I've got some data system, like I've got a bunch of people I need to model. I can go struct person, okay? And each person might have a bunch of attributes that are low-level types. So they might have a name, which is a string, and they'll have an age. What's an age? Is an age going to be int or a float? What's that? Pick one. Int, yep. So cool, this is a data modeling problem already. You can already see that when this person someone has to do an insurance calculation with this type, they've gotten it wrong, you know, because they're 38.5. Name, age, I don't know, height. We can model that as a float, 64. Cool. So this is how you define a little thing in Julia called a struct, and this is our own special composite type based on primitive types. You're going to do much more of this later on. So person is Kevin. Oh, it's hard to come up with a name. His age is 34 and his height is 177.0. Okay, so we can say, in Julia, we can make this thing. Okay, cool. Kevin, that's Kevin. And then we can make, say, Mary. Her name's not Kevin, it's Mary. She's 43 and she's 167. So we've got these two things, type of Kevin, it's a person, type of Mary, she's a person too. We can make an array of people. We can go Kevin, Mary. Cool. There's an array of people. This is a thing you can do in Julia. I was talking about multiple dispatch and I was confusing you all before. I'll give you a little bit of a hint about how multiple dispatch can work in Julia to do really powerful things. And I'm doing this, predicating this on as a data modeling exercise, okay? Some people might have noticed base.isLess. Has anyone seen that come up when they're doing the sorting stuff yet? You were asking about it just before the lecture. So isLess is like this idea of if I have two elements, I want to define what the difference, isLess is a built-in function into Julia. So, okay. Returns true when T1 is less than T2 in lexicographical order, or if you've got numbers, it depends on the type, what this thing isLess function is. There's not going to be, because person is not a built-in type in Julia, we can override that with our own thing. We can go base.isLess. We're going to do an inline version here. X is a person. Y is a person equals isLess. Bear with me here. We're going to be ageist. If we're going to sort people by age. We're going to say a person is less than another person if their age is less than them. I'm sorry about that. So that's what's going to happen. So what I've done here is an inline function where isLess will not exist for the type person in Julia because I made this type just now. So I can go, well, what I'm going to do is I'm going to get the fields of this type and define my own and just use the base isLess on age. Now, this is kind of magic. We had this array of people before. We can go, without having to write any code, we can sort data. Ah, that works. Yep.
What is base dot do?
Base is the base module for Julia. So it's all the functions that are imported with when you start a Julia session. You get all these functions. Anything I type in here, like plus is part of base. So when you'll do modules later on, don't worry about it too much. But this is a bit of Julia magic. So your question before about why would I do type annotation? It's for doing this, where I want to extend a method beyond where it's you would expect it to work. Sort doesn't know anything about my type person. I just had to redefine one function, and then I can get sorting to work on this new type, and it will be super fast. That's I just jumped ahead 3 weeks, 4 weeks in the lectures. I'll pull back now. That was just for you. But kind of this data type here where I said Kevin, he's got older. Age equals Kevin dot age. It's no, you can't do that because it's immutable. So it won't let me update any of these fields. I can define a mutable struct where you're allowed to change the fields. But then you got this other problem where cool, a person has only got 3 fields, right? And they've also got an address and they've also got this other thing and they've also got this other thing. And I'm too dumb to think of all these things before I start writing my code. I want a data type where I can make all these fields and I can change them and I can edit them and everything's going to kind of make sense. And that data type, it wasn't all for nothing, is a dictionary. So I can make an arbitrary, semi-arbitrary, I'm going to go dict has name, Kevin, age, I can't remember what I said Kevin was. Height. Okay. So this is the much more flexible, but less well-structured version of this is this thing called a dictionary where you have a bunch of things called key value pairs, right? So each key is this thing, I've made them strings, but they don't have to be strings. They can be any data type you want. The only thing is each key has to be unique. You can't have name in there twice, that doesn't work. But each key goes to a value. So this thing, if I want to go, what's Kevin's? The access pattern looks a lot like arrays, right? I'm going to go, The thing I want to be fast is looking up a key and getting the value back. I want to know, what's Kevin's name? Type name, Kevin. And what's Kevin's height? He's 177. And what's Kevin's age? Cool. And that's Kevin's height is growing. Then Kevin got bigger. So this is much more flexible, right? And we can add more keys. We can add more keys to this dictionary. We can do whatever we want with it. Consequence is it's never going to be as fast as the built-in structs. So there's this, when you're working out a new bit of code, you're going to go like, I want this flexible thing. Then when I understand the problem a little bit better, I'm going to bed down these types a bit more. I might think about making a struct or a named tuple to deal with this. Okay. What did I say here? So you can start with an empty dict and you can add things to it. So this one, okay, we got, yeah. I guess for Kevin, I can do, as long as the key doesn't exist already. Kevin. Now Kevin's got this extra field, misspelt address. Anyway, you get the idea? It's really cool, right? Like this is like a super flexible data structure that lets you do a lot of stuff, lets you model data really powerfully. And you would have seen that when I did get the Shakespeare data, it came back as a dictionary because there's this thing called JSON, JavaScript object notation, I want to say, that is basically a dictionary of base types. And then this is this thing. It's like if you've got a dictionary, you can do all this stuff. Useful function for dictionary, keys for Kevin. He's got a name, height, address, and age. And I'm going to get the values for Kevin. His name's Kevin, 169, St. Lucia 34. Now, okay, what do we do here? So we've got a slightly funny example here, thinking about how you might make this, like we don't know anything about what Julie is doing to make a dictionary under the hood, right? So basically the most naive implementation is an array. We've already seen an array. We can just use a bunch of arrays, and arrays will be, here's the key at this index, here's the two arrays, here's the key at this bit, here's the value at the other bit, key, value, key, value. We could just do this by, if we get a new key and a new value, we just push them to the array. Yep, add key value pair, you could do this. So the question would be, what's the computation? If I did it this way of arrays and I'm just pushing to it, what do you expect the computational complexity of checking whether a key exists in the array to be? You got to search through the array, right? Yeah, so you got to look through every element of the array and check, is this key in the array? Is this key in the array? Is this key in the array? Tricky thing is, so that's order n. Oh, it says down the bottom, blah, blah. So that's not cool. That's going to be really slow. Like, especially if you have a dictionary that's like got a million things in it, like check a million keys, like you don't want to do that. Based on a slightly magical thing that's the way this is typically implemented is this thing called a hash function or a hash table, which is a special data structure. This is almost, it was usually order 1, but sometimes log n-ish. There's a thing called hash collisions you can have, and you have to check for that. That can make it a bit messy, but most of the time, checking for the inclusion of a key is really, really fast. So much, much faster than this naive implementation of an array. And if you're really interested and you want to bend your brain, your lecturer, other industry lecturer, Andy Ferris, has done his own crazy implementation of dictionaries in Julia using an alternative thing that you can go and watch this YouTube talk if you want to see about how that's actually implemented. So then we've got another one. This one might be useful for your homework. I don't know if you've got and it's a useful collection for mathematics is you can actually do a set. So, oh yeah.
Sorry, for the dictionaries, if you make a mistake, like you missed it
G in the key.
Yep.
Is there a way to readdress that?
Yeah, you can, I think it's delete that. What would it be for a dictionary? I can't remember. There's one for deleting a key. I'm pretty sure you can do that. So that's fine. There's a way, and I can't remember exactly the thing, but yeah. Delete that's for I want to see if that actually works. I'll be wrong. No. Anyway, we can look that up. So if someone wants to look it up on the internet, it'd be like, how do you delete a key from a dictionary in Julia? There'll be a way. It's fine. They're super flexible. So, okay. So the next thing you kind of get is like a set. So what's the difference between a set and an array mathematically? I want to think about it. Like what's the big defining difference? Yeah, that's right. So I meant to say that. So one thing of dictionaries is that the keys in the dictionary are the elements of the dictionary are unordered. If you iterate through a dictionary, they won't come out necessarily in the same order you put them in. They'll come out in a random order. So they're not like an array. And this thing of a set, like I said, for a key for a dictionary, like you can't have the same thing twice. You only get one key. If you put that key in again, it'll override it with the new value. So you kind of get sets for free by dictionaries. A set, the way you would make the data model for a set is basically a dictionary with keys and no values. You don't care about the values, you just care about the keys. And the keys are the elements of the set. And then you can use all the machinery you built to make your dictionaries you do set stuff. So you get, because it's useful on its own, you can make a set. And again, basically, what's the thing you always want to do with, there's a couple of things you want to do with sets. What would be one thing you want to do with a set? Take the union. That's cool. So let's go that. So this thing you'll notice, so we put repeating elements in the set, and what happened? 1, 2, 3, 4 is all that ended up in there because we repeated. So let's call my set is that. My set 2 equals a set. Just make it really obvious that they're different things. And 3. So we've got my set 2, union, my set, and my set. Oh, can't type. So that's the union of those two sets. You notice that it kind of messed with the order because there's no order to a set, how it's decided to keep those inside. You could do the intersect. There's only one thing. Hopefully you guys could see that when I set that up. My set 2. So the intersection is just that singular element 4. Yeah, so you can do that normal set thing. The big thing you want to do though is I want to check if B in my set 2 is true. I can check if 27 is in my set 2 is false. And this set inclusion, exclusion stuff, you want to be super fast. So the fact that it's unordered and using this hash table underneath to be really fast for lookups means you can do, if you have a data structure where you don't care about how they're ordered, you just want to check if something's in there, a set's a really good one to use. But it's kind of like you may as well do a dictionary if it has any other attributes coming along for the ride. That'll be your key value pairs. That's a set, and you get all the useful, there's a bunch of stuff here. You get set diff too. So this has sidedness to it. So, depending on which one you put on the left and the right is the way it will do the set diff. If you want help with that, yeah, just go look it up. So it's the construct the set of elements in S, but not in any iterables, blah. So it's iterating through the ones in this one, checking the set diff. So this is just a hint about how you do all these things. So the symmetric difference, anything you'd want to do, that's a set. Yeah, so what would you expect? It's this set inclusion thing. So there's a bit more of a thing here. So what we're going to do, this is your intuition before, is like if you had to go through an array and check one by one, is this thing in there? You know, there's an order, you can't, and you don't have this fast lookup for a value. So this, you can think of an array as like the key, it's a dictionary where it's like 1 is the key and the ith element, that element is the value. But for in terms of the, if you don't care about how they're ordered inside the set, then you wouldn't do that. You would use a set. So this is just a simple example where we've got data as an array. There's 10 to the 5 elements. Let's just do this. So it's a big set. Hopefully it didn't shrink. No. So there's a chance there, if anyone wants to go and do a bit of probability theory, if I'm drawing random numbers, 10 to the 5 random numbers from int32, what's the chance that there'll be 2 keys with the same value if I turn these into a set, like 2 set elements? Like, what's the chance? They end up being the same size. So if you're unlucky, you might end up with less elements because it drew the same one twice because there's only a finite number of int32s. So we've got a big array, and what we're going to do here is we're just going through, we're just going to check while true, do this timing thing where we're going to go check between these 2 different array functions. This one is the element in the set or is the element in the array? So you get this function, that's just in/in, if you want to see what that is. That's just the same thing in, it's just a different syntax. So if you just want that LaTeX, if you want the LaTeX thing, it's -in, press tab, and you get that one. So that's just checking whether it's the same thing as doing in, but just looks a bit more mathsy if you want to do it that way. So what we're going to do is we're just checking whether this value is in the array, and we'll count it. We'll check if the value is in the set, and we'll count it, and we run this timing. And you see this difference here. It's quite astounding difference of like 4-ish seconds versus 0.01-ish seconds. So it's like heaps faster to check whether an element's in a set than it is to check whether element's in an array for a big array. That's the reason you would use this one. Has anyone seen a homework problem this could be useful for? If you've got a data model of a thing and you want to check whether a thing's in the other thing, so like set of prime numbers, maybe that's a thing. That's a hint. You don't have to do it that way though. There's a better way to do it. But that's that's an example for you guys where a data structure, you know, just checking inclusion can make the operation really fast. You can use the built-in machinery. Okay, cool. Where am I up to? So where you're going to get a bit more of this, especially later on, you're going to do something called a priority queue. I think you're going to write the heap yourself. But there's a special data structure called a heap. It's a kind of a weird name. We're going to use it. So this is like, we'll go back, we'll just pretend we've got arrays. If you want to sort an array, can anyone think of a data structure type trick that could make it fast to check to sort the array? Like if you know the next thing I'm going to do with this array is sort it, what could you do when you construct the array? Weird question. Do you get it? Anyone? Yeah, put it in order. That's exactly right. When you're constructing the array, especially if you're constructing it one at a time, you can find where this goes in order and just put it in there. So it's already sorted. Then you've got order 1 sorted because it's already sorted. If that was all I was ever going to do, I can just make it sorted in the first place. Nothing to do, no work to do. Seems like cheating, but that's the idea with data structures is like, can I do something when I make this thing, do a little bit more work up front, and then it makes the operation I'm going to do on it trivial. That's the big hint with data structures. So like there's a bunch of basic data structures. Thank you for the chat. That's great. Yeah, that's exactly right. So There's a bit of overloading of terms with heap. There's a thing about memory that's called the heap, but this heap data structure is this hypothetical thing. What do I want to say? So a heap is, got a bit of a COVID flavored example about people entering a vaccination center. So this thing of like, a really useful thing is you want to do a priority queue. Like if you've got a queue, you kind of don't care about the whole structure of the queue. The only thing you care about is who do I serve next based on some priority, right? That might be a thing you want to do. That's a really common problem. Like Andy can talk to you at length about this stuff with the work he does at Alara. A lot of that stuff about doing simulation is like, you want to know what do you simulate next when you're doing a dynamic simulation of something through time. So this useful thing is like, you just want to be able to, if I have this data structure, we'll try and base it on like, what kind of things do we want to do? We want to add people to this data, add things to this data structure. We want to remove the one with the highest priority. These are the two kind of moves we want to do. And the third move is we want to modify a priority. This thing's called a priority queue. There's lots of different ways you can do this. Usually a heap is the one, a heap underneath. And there'll be a bunch of ways you can implement this. So this is, again, before I was talking about structs. So if you don't want to go to another way of like, you know, the third option, I said you could do a dictionary, you can make your own custom struct. The third option is this name tuple thing. We can go, let's make a bunch of people. There's a person A, they have a priority 23.2. Person B, they have a priority 26. This thing, if we're going to go type of person A, it's a name tuple. So again, another thing like a struct, like a dict. It's another thing, various reasons why you would or wouldn't use this. If you want to access this guy, you do dot name. So this is more like how you access the fields of a struct in Julia, not like how you access a dictionary. Remember I said for a dictionary, you do this guy, you put these square brackets. For a name tuple or a struct, you do person A dot name is Zach. Now, the naive implementation, we can use push, right? So we get a new person into the queue with a high priority, James Yarden. And so we got this array. So again, oh, this is a mouthful, this one. So what I'm doing is I'm making a naive priority queue that's just an array. So ignore the heap for the moment. Again, you can do this with an array, it's just going to be slow. You just have to search through. You can do all these operations we said we'd like to be able to do. With a priority queue, we can go, cool, there's this naive, we're doing this, this is all this stuff. So the type, we're making an array of type name tuple, where you have a priority and you have a name, and the value is going to be a float 64 and a string. That's what that does. So we can push, because it's an array, new person. We can push, they were called new person, weren't they? Oh, sorry. Silly. So naive priority queue is this a funny array thing, and we're going to push a person to it. So there's one person on there now. There's another person now, person A, person B. So we can put, you know, people are arriving, they go in the queue. It's just an array. That's that guy. An array of name tuples where the names are priority name and the values are float and string. Cool. Push, push, push. You can add more and more people. Push could be complex, you know, because we said an array, everything's going to be next to each other in memory. It might not be a good idea to do that, but it's kind of fine if you don't get a choice. Every time you remove an individual, you can use this delete at thing. So that works for an array. So if you want to get someone out of the queue, we can find the index we want. So this one will work out for this one. So we want to get rid of person 2. Zach's gone because for some reason they jumped out of the queue. That's fine. Yeah, and again, this problem though, like again, it's going to be order n again. So we kind of got the worst of all worlds, right? Like it's going to be slow to put a new person onto the array. It's going to be slow to find the person with the highest priority. Deleting it's probably okay. That one's going to be fast. So again, this one's just a simple get next person. Again, for the question earlier on in the lecture, you can do all this type annotation if you want to. You don't need to. It's good to see it though. So basically, if you see these 2 ellipses, it's just like, that's just saying what the type of this thing is, and it will stop this function running for any other variable I try and put in. There's not much reason to be doing this, but good to see it. Assert that it's not an empty priority queue. We're going to get the first person off the queue. So for any array, you can do this first. You can get this guy, so that's Yarden. And then you've got to go through and you've got to go for P in priority queue, check if it's the biggest. If it's the biggest, max P is P, return the person with the max. Yep, that's that guy. So that will return the max person from the queue. That sucks though. Again, yeah, so if you don't mind how slow it, like if you're not really ever adding people to the queue and you're just trying to get the ones off in order, or they're never going to change, it's not so bad doing it this way, but it's kind of terrible. What we'd really like to do is use a data structure that will make our life easy for us. So what we can see, this is the cool thing about a heap, that finding the maximum is order 1. You can always get the thing in the heap with the highest priority or the max value or the min value, whichever way you set it up, is order 1. So that's really fast. That's cool. I'm not going to go through how you implement this. It's just a thing that exists, the data structure. You can get an idea of underneath, it's a tree-based data structure where there's some splitting and you've got some, got a root node and then some leaf nodes down the bottom, and it will give you an idea of how to traverse this thing. You're going to go, I think you get to implement this yourself, so this will be fun. But you can just use the base one. Here is, so what we get though, with a heap, deleting is a bit more costly. Deleting an element is going to be log n. Insertions are going to be log n, and updating a priority is log n. So you don't have to go through everything. So you get this tree-based data structure, so it's kind of fast to traverse to get to the bit you will care about. Then you can do it. But again, we'll just worry about it as a black box. And then you can see this is like a bit less dumb than the suggestion, hey, let's just sort the array and just take it off that way. Because we can always get off the max and then delete it. This is like a really simple way to do this with a slightly clever data structure. So the moves in this guy, I'll just check I got this. Cool. This is an implementation of heap sort. We're going to set up a binary min heap. So that's a special data type from data structures. It's a type of heap. You also get a hint there that there's a min heap, there's also a max heap. Binary min, and there's a min max heap, just to be confusing. If you want to see what this type is, oh, no documentation. So you got to go and look in datastructures.jl, because as soon as you get out of base, the documentation gets a little bit worse. But what we've got with these moves is we've got insertion, we use push. So if we take an abstract array in, we're going to push them into the array. Each one of these is going to be order log n. And then when we get them back out, we do this pop operation. We've got to do this for each one. So that's actually, that comment is burning in my brain because it's wrong. It's order 1 for each one of these. So what we're going to do is we do the log n, and then we pop them out and they're fast. So you get them back out in order. So let's just see if we can see that. I'll just do it one by one. So we've got this heap. Oh. Okay. So if I go push HA1, H is updated, push HA2, push HA3, push HA4. Now if I go pop from H, it's going to bring off the top one of those. So you get A1, but pop, remember, if I've got this exclamation mark, it's a hint that it's editing the thing underneath my feet. As soon as I pop this thing out, it's not in the heap anymore. So it's like I push them in and it will create this tree data structure that gives you this efficient traversal. Pop, pop, pop. Nothing in there anymore. So you tried to get I only put 4 things in. I tried to get more out. There's no more out. So you get an error. So you have to be a little bit careful there. So this is really simple, right? Like, so we make this heap data structure. We get these built-in functions push, which is probably quite complicated to actually implement, doing this rebalancing and making this tree-based data structure. Then when we pop this off, we get this thing. So this is a really simple way of using a data structure to give you sorting much faster. So it already ran everything for me. So let's make it again. And we'll go heap sort data. So if we look at the code, what it's going to do is it just takes this array, it pushes these into the heap, and then it just reads them back out of the heap. And it uses the data structure to do all the sorting for us. And this is fast. How fast is this going to be? Let's make some data. I've still got a bubble sort, I hope. Bubble sort, there we go. X equals rand. Let's go random seed 0. X equals rand n 1000. Bubble sort. Hope I didn't make this too big. Okay, so that was about the same timing as we got last time. Well, not that one. So I've got to regenerate it. Random seed. X equals rand. Then we're going to time that. We've got 0.15 seconds. We've got our heap sort now. So X, we'll just regenerate this set. Moment of truth. At time. Whoa. A lot faster, right? But not much code. We just use the inbuilt data structure to make our life a lot easier. So we're using this heap data structure, and it's like the basic idea is simple. It's like if it was an array, if I just pushed it in order, and then I read it off, it would be really fast. But because pushing it in order for an array is hard, maybe there's something more clever we can do that can keep the type priority at any point. And then when we pull it off, it'll be much faster. That's this heap sort. Hopefully data is actually sorted. Oh no, data is really short. I cheated. No, it's not as big a win, but I was a bit surprised. I was like, oh, suspicious. Yeah. So that actually no, we got the first time. Sorry, I lie. Let's just be careful and do the timing again. Yeah, so it is much faster still. And X should be sorted. Yep. Cool. So it's way faster than bubble sort still. And it has, so if we go through and we're careful about keeping account of how long what the order of is of putting something in and what time it is to pop something off. So if we're going through all this, it ends up being in log n, which is like the scaling we saw for quicksort. That's almost no work, right? So we can do this timing. This is pretty terrible timing code here. But, you know, there's a bit of overhead with memory and memory allocations with this guy, which is a practical reason why heap sort is not the one that tends to be used. But it is, it's a good educational one. You go like, here's a useful data structure, a heap. You get these operations, you do some funny tree-based thing underneath it and it lets you go much faster. It's not going to be, so here's some realistic timings. We're going to do heap sort on 1,000,000 points and we get it in 0.3 seconds. We do heap sort with the we use the built-in sort, which is based on quicksort, and we get about 0.1 seconds. So it's about 3 or 4 times faster, even though they have the same asymptotic scaling. because of this memory allocation thing with heaps. Cool, and that's what the plot looks like. So they both should scale up the same way, asymptotically the same complexity, but the built-in sort's still winning. So I think that's probably a good time to stop. So next lecture, I'll talk about really quickly, really quickly, because this is like for you guys to go through, I think, of two algorithms. The big problem with heap sort is this memory allocation problem. You're going to have to allocate memory. Can you do an in-place version where you're not actually writing over we want to just use the array we've got? And can we use the similar idea of like, be clever and never do things more often than we have to reduce the complexity of the algorithm? And the two that we'll learn really quickly, I'm just going to sort of talk at them and you guys can go off and learn them properly yourselves, is merge sort and quicksort. Based on this divide and conquer strategy. Yeah, that's where we'll get to next lecture. I'll stop it there, I think, unless anyone has any questions for now. No? Okay, thank you.